Good morning. I am very happy to present Dr. Bhavya Lal, Associate Administrator at NASA, and she will be discussing nuclear propulsion for Mars. Welcome, Dr. Lal.
Good morning. It's an honor to be here. I'm here this morning to talk about nuclear propulsion to Mars, and I'll try to speak for about 20-ish minutes, and hopefully we'll have some time for a good discussion. I'll talk about 5 things. What are nuclear propulsion systems, just for us to all level set? Why would we want nuclear systems to get to Mars? What's the plan? What are we thinking about? What are we currently doing at NASA, and what challenges do we need to overcome? So again, level setting, you all know what nuclear propulsion systems are, but there's 2 variations. Nuclear thermal propulsion systems are very much like chemical systems, except we have now separated the propellant from the heat source. So, nuclear reactor heats up, let's say propellant like hydrogen, it exits out the back at very high velocities. As a result, and since hydrogen has such a small molecular weight, it's able to, the rocket equation will tell you that it provides a very high ISP, twice as much specific impulse, twice as much as chemical systems, and that's a good thing, and we'll talk about why. NEP, nuclear electric propulsion systems, are a little bit different. In fact, they're very similar to reactors on Earth, where you use a nuclear reactor to generate electricity, and then electricity is used to accelerate charged particles, an atom like xenon, again out the back of the engine, creating very high levels of specific impulse. So NTP offers impulse levels, as I said, of twice as much as chemical systems, and with NEP you can get a specific impulse that's 5 to 10 times that of chemical systems. Of course, the difference is that with NTP, you get very high levels of thrust, similar to chemical systems. With NEP, at least for the moment, thrust levels tend to be lower, although there is no physical reason why it cannot be higher. If you have very high power reactors, you can have similar levels of thrust. So there's no physical limitation to, or physics limitation to, getting high thrust out of NEP systems. I actually took this picture, which is on the right side, when I was visiting Marshall many years ago. And it was kind of a reminder for me that nuclear isn't a new thing. When President Kennedy talked about, went to Congress to ask for funding for Apollo, he actually specifically asked for funding for nuclear propulsion rocket and NTP system. And what I find interesting on this poster, which I took a picture myself, is number 1, taking a man to the moon and bringing him safely back to Earth, accomplished. Number 2, it's still overdue. And then, of course, number 3 and 4 were other things that we also got done. So it's something we started thinking about right at the dawn of the space age. We just haven't closed the loop. So I guess the question to ask is, well, why do we want nuclear systems to get to Mars? And I said a little bit earlier, it's the specific impulse. There's really nothing magical here. Nuclear propulsion gives us better gas mileage. So the higher exhaust velocity of the propellant in NTP systems will allow for much less use of propellant, which of course is a good thing, because 1, it reduces the cost of launching all that propellant. And even if launch costs are going down, as they are, there is still a huge amount of logistical integration that needs to happen if we have large amounts of chemical propellant that needs to be going up. So it is, and because of the high thrust that NTP systems allow, you are able to transport humans, which is actually important, because when we are in the high radiation environment or 0G or other factors of space, we want to get to places fast. And of course, depending on how you pick some orbits, and actually Pam Milroy, who goes after me, is going to talk a little bit about how we're going to get to Mars. There are some high energy orbits you can use because you have nuclear propulsion systems that will allow you to get to Mars and back faster. Similarly, as I said, for NEP systems, the higher ISP allows you to again have much better gas mileage, but because of current systems having lower thrust levels, it will not be very fast, at least for the moment. And so NEP systems would be really great when we want to take cargo, where we can be slower, but we can take a lot more for much less amounts of propellant use. So ultimately, what nuclear gives you is better gas mileage. You have a Prius, and you can do so much more with it. So can we go to Mars with chemical propulsion? Of course, we can. If you want to go across country, horses are just fine. But, it's nice to have airplanes. We can do so much more and have so many more opportunities, which is essentially what nuclear propulsion does for Mars as well. We don't want just to go to Mars, right? Nuclear is a capability. It's a national capability that allows us to do so much more than just going to Mars. It allows us to go to, interstellar places, right? So, as I said earlier, even if launch were free, chemical systems have challenges. And it's just something, it's a national capability we need to invest in, almost independent of the need to go to Mars, although obviously it is very core to our getting to Mars. So what is our plan currently? For the moment, we have not made a decision how we will use nuclear to get to Mars. And there are lots of trade studies underway. So we are looking at chemical, we are looking at solar, electric, and chemical hybrid systems. We are obviously looking at NTP and NEP combined as a hybrid with chemical, because as I said earlier, with current power levels of NEP systems, the thrust levels would be too low. So from a mission pool perspective, we are still figuring it out. From a tech push perspective, NASA is actually wanting to invest both in nuclear electric and nuclear thermal propulsion systems. And just recently, the National Academies wrote a report in which they gave a similar recommendation that we do not know enough to know which of the two systems are the ones we want to be using to go to Mars. So we need to invest in both to be able to make that down select a few years from now. We would like to, and again, I'll talk a little bit more about this in later slides. There are other parts of the government that are developing NTP systems. We want to collaborate with them. We want to make concurrent investments in nuclear electric propulsion systems. We do want to continue to support chemical systems, obviously. We also want to be investing in next generation systems, whether it's nuclear fusion or it's what are called liquid core nuclear thermal propulsion systems, where it's no longer a solid fuel, it's liquid that allows for much higher levels of ISP and other advantages. So that's kind of what we want to do. What are we currently doing? We are primarily investing in nuclear thermal propulsion today. We want to be making, multi 100 megawatt, and I think we're looking at about 500 megawatt thermal systems using what is called high assay low enriched uranium reactor. And high assay low enriched uranium, as many of you may know, is uranium enriched to around 20% enrichment. In the old days, we used what is called weapons grade enriched uranium. And I think in 2020, there was a presidential memorandum. And I think earlier there was a question around policy issues, and I'm really excited about that because I'm going to get into some of those policy issues. So there was a policy decision that was made that unless there is a good reason to, we want to be using low enriched uranium or high assay low enriched uranium for our system. So that's what we're working on. And that's where there's a lot of new data that's needed, because all of our previous data, from the rover days, from the days when we did invest in NTP in the 1960s and 70s, we had been using highly enriched uranium. So that data doesn't fully translate, and a lot of experiments that we had done before need to be recreated. NTP requires very high temperatures, 2900 Kelvin, 3000 Kelvin. We do not know, those materials don't yet exist. There's a lot of research that needs to happen to make sure that we develop those materials. There's a lot more we need to do in terms of manufacturing systems that can handle that kind of flow rate, that kind of temperature that an NTP system entails. We need to be doing some subsystem design and building to just understand how some of these things work. We need to be doing some ground testing, and actually that's pretty complicated because Again, in the old days, we did a lot of these testing outside, with all of the exhaust going into the air. We don't do that anymore. So we need to think about how we might do ground testing. And there's some really interesting emerging ideas on, can we just test some of these things in space, never doing a ground test? Again, a lot of debate in the community as to how we might do that, but a lot of really interesting new innovative ideas as well. And then, of course, since for NTP, we are currently thinking of hydrogen. And as you know, well, hydrogen is a tough element to deal with in the cold of space. So there's a lot of cryogenic fuel management research and investing that NASA is doing. On the NEP front, I don't want to spend a whole lot on this, mostly because as per Congress, NASA should be investing mostly in NTP. So for NEP, we've done some very low-level experimental work either in-house or with universities. So a lot more needs to be done. In fact, the National Academy's report I had referenced earlier had made the point that if you want to be going to Mars with NTP systems, it's feasible in the 2030s with aggressive investment. But with NEP, our investment levels in the past have been low enough that even with aggressive investment, we are not going to make a mission to Mars in the 2030s. So we just need to do a lot more with NEP than so as to make sure that we have enough information about both NEP and NTP systems to make a down select. So what have we done in recent months? For NASA is actually not just investing in propulsion systems, we are also investing in surface power. We are looking at having a reactor on the moon, for example, for heating or providing electricity to human habitats, for ISRU, in situ resource utilization, all sorts of, you need power, right? And so we are working on developing power systems for the moon. Of course, they translate to Mars as well. Obviously, Mars is a different environment. It's a CO2 rich environment, not like the moon. But there's a lot of parallels, and those are some of the things that we are going to be looking at. So we have there has been some work done at the White House on how we might provide launch approval for nuclear systems. So NASA has revised our internal safety protocols to accommodate this policy called the NSPM 20. We have developed, working together with other government agencies, DARPA in particular, we have developed technology roadmaps for fission systems. And actually, we just recently completed a report on how we would use propulsion and power systems through 2040. And all of these reports are available if you would like to see on our various websites. And if you don't find them, let me know and I'll make sure you can get them. For surface power, as I mentioned, we are looking at a 40 kilowatt electric system. Again, low enriched uranium. We are looking at different aspects of the reactor, moderator materials, and we have completed work with industry in recent months to develop better designs. And our plan is to go to the next round of solicitations to industry to begin to do the next level of work. On thermal propulsion systems, again, we have selected and awarded phase 1 awards to industry for designs. We have been working with the Department of Energy to fabricate and test some specific kind of fuels. As I mentioned, the fuel for nuclear thermal propulsion systems has to be able to withstand very high temperatures. So we need to develop some of these, the fuel forms. We work very closely with Idaho National Lab to do some of this work. And we have been working with DOE and industry in completing preliminary feasibility studies. On NEP, as I said, not a whole lot going on other than thinking through some technology maturation plans. I mentioned our collaboration with other government agencies. DARPA is an important collaborator. DARPA is thinking about developing an NTP system for fast maneuverability in cislunar space. Obviously, they are looking for different applications than NASA is, but there's lots of common areas of interest. They are looking at a lower ISP system than NASA would like. So in other words, their fuel doesn't have to go to temperatures as high as the fuel that NASA would like, but nonetheless, there's lots of really important areas of collaboration. We had a memorandum of understanding that we had signed with them last year, which is being updated to include some new thoughts, new ideas on potential collaborations. The Air Force Research Lab is looking at nuclear electric systems. As I said earlier, NEP systems are important for NASA. They are really helpful if you want to go deeper into space for robotic science missions where speed isn't as important. And luckily, NEP has its AFRL has interest, and we are looking at potential collaborations on NEP with AFRL colleagues. Again, within DoD, there is a strategic capabilities office goal. They are developing a small modular reactor for forward bases. And again, as you can imagine, for NASA, lightweight small reactors are very important. And again, terrestrial reactors are different than space reactors. However, there is a lot of commonality that we need to leverage. For example, fuel forms might be useful for us to commonly develop. Last but not least, and in fact, one of our most important collaborators is the Department of Energy. DOE has labs. They have decades of experience developing nuclear systems. They are actually looking at some really interesting new ideas like 3D printing nuclear reactors, which is just transformational. Again, it's a little bit out in the future. I see Jim smiling. I don't know if he's excited smiling or if he's so there's a lot of really important collaboration that we are doing across the board with government agencies. And as I said, we think of nuclear as a national capability, and it behooves us to work on it together, not just with other government agencies, but also with the private sector. And we have been doing that. So what else is going on? And here I come up with some of the policy issues that I think had come up earlier. Actually, before I even say that, I'm just so excited to report that in the 23 budget, for the first time in many, many, many years, the president's budget included funding for nuclear propulsion. In previous years, it has been. And this is thanks to all the effort that our Administrator Nelson and our Deputy Administrator Milroy made in terms of helping the White House understand the relevance of this capability for the nation. So again, other policy on policy front, I mentioned NSPM 20. This is a presidential memorandum on launch of spacecraft containing space nuclear systems. There was actually a policy in place before, but it applied primarily to radioisotope thermoelectric systems, RTGs. And we weren't really sure how they would apply to fission systems. So the policy was updated to include fission systems. And also what's really interesting about the policy is that it quantifies launch risk based on the characteristics of the system, level of potential hazard, and national security considerations. So it's a tier system, which really makes it possible for us to have different levels of approval for whether you have a little tiny a radioisotope heating unit, which is only a few grams of plutonium, to a nuclear reactor with many hundreds of kilograms of uranium. So it really does give a path forward. And we always, whenever we talk about innovation, we're always talking about technology innovation, but I believe that NSPM 20 is actually a policy innovation. Because of this document, there's a lot more industry interest in developing nuclear fission systems, because now they see a path forward. Now they think they can be involved in developing technology and ideas. Another part where we've had policy guidance for nuclear is the 2020 National Space Policy, which says the United States shall develop and use space nuclear power systems where such systems safely enable or significantly enhance space exploration or operational capabilities. Again, these are very, almost boilerplate words, but they're very important because they give us, they give us top cover. They give us a sense of direction. Another piece of guidance that came from the White House was what was called Space Policy Directive 6, SPD 6, which is a national strategy for space nuclear power and propulsion. It lays out a strategy for the responsible and effective use of SNPP systems, and it specifically actually points to highly enriched uranium systems. And it doesn't ban them. It doesn't require that we use high assay LEU systems. It just says the use of highly enriched uranium in SNPP systems should be limited to applications for which the mission would not be viable with other nuclear fuels or non-nuclear power sources. So they give us the alternative to use HEU if we need to. They just have there's just a sense that it may be easier for us to work with nuclear systems. For example, we can involve more of industry and have more international collaborations if we are using low enriched uranium systems. So that's not all. There was also an executive order on small modular reactors in 2021. And this particular executive order talked about government agencies, including NASA, defining requirements for utilization of nuclear energy systems for human and robotic mission through 2040. And it also said there is a need to develop a common technology roadmap through 2040. So lots of White House policy guidance. We have had incredible legislative support for years. There's an annual $110 million appropriation from NTP for NTP. There are frequent congressional hearings where Congress wants to know, what it is that NASA is doing. And the 2022 Authorization Act specifically includes a section on nuclear power and propulsion. Internationally, also, there is a lot of guidance. UN Resolution 4768 lays out principles relevant to the use of nuclear power sources in outer space. And there's some weirdness in it, but we can talk about another point. The weirdness is that it says that we can only use HEU in nuclear systems. I think there's some, I have some ideas on why it says that, but these are solvable problems. So there's lots of policy guidance, there's funding. I mean, obviously there could be more funding. So what are some of these challenges that we need to overcome? And again, just to make the point that, over the years, I said, this is not new. Over the years, we have spent, depending on who you ask, about $20 billion on developing propulsion systems and propulsion and power systems. However, we keep starting and stopping. And I think that's our challenge. My view on the challenge is that it's a chicken and egg system. Our human exploration folks have not yet said, hey, we would need a nuclear propulsion system that has an ISP of X and a thrust of Y and a time frame of Z. And because there is no mission pull, we have not had as much technology investment. And of course, the egg portion is that because there's no technology investment, there's no, mission planners are afraid to ask for specific systems. So I think we need to break the cycle. That, in my mind, is the biggest impediment to developing a propulsion system. I think we are there. I think with the president making a request, with Congress being supportive, with all of this policy guidance, I think we are starting to break that logjam and moving forward. There are some other impediments as well, but I think they're all solvable. There are some disagreements about whether we want to move forward with NTP or NEP systems. Again, both have good pros and cons, and we need to work through those. Again, up until recently, there were some, there were policy impediments, but as I said, we are trying, we are getting over those. And again, up until recently, there was not as much commercial involvement. And again, having commercial involvement makes things so much more exciting and interesting. And there's, new funding that, that government doesn't need to, government can have help. And again, I do want to make the point on the right that actually the use of nuclear power is not settled. There is legitimate competition from chemical and chemical solar alternatives. So we really do need to look at all of these opportunities in the same frame. There's no silver bullet. We need to do a lot of things at the same time. We need to make the case. We need to tell why is nuclear enabling. I think I started to do a little bit of that, but we need to do a lot more of that. We need to have our decisions made by strategic factors, not just technical ones. We need to kind of start small. I think we always try to go to the best and the best system ever. We need to kind of start with something smaller, do demos, collaborate more with others, and see where we get. We need to start to test an emerging regulatory regime. We need to be a little bit more transparent about our budgets and acknowledge that it is very difficult to predict budgets for systems which we have never built before. We need to learn lessons from other domains. The RTG world is a really important way for us to think about how we might develop fission systems. We shouldn't overpromise. That's a recipe for cancellation. And there are some remaining policy issues as well. For example, how do we think about operations issues? How do we think about decommissioning, because the policy guidance we have is mostly on launch. Let's not forget to address public perception issues. Nuclear does have that. With that, I will end my talk, and I'm happy to take any questions.
We have time for one quick question.
Hi. Actually, I have two. I don't know if you have time to answer, but one is, I understand in the 70s or so that this program was stopped because of public protests and concerns about a launch failure. And how are you going to address that? I know you briefly did, but the second is, I understand from Dr. Zubrin that the reason we don't have fusion energy at this point is more of a policy issue than a technical one. And I wondered if you agreed in that. It seems clear to me that we're not going very far from Earth, and we're going to solve climate change anytime soon without the use of nuclear power. Thank you.
So actually, the NSPM 20 actually does precisely that. It lays out what are some of the maximum levels of performance for the rockets, the maximum levels of radioactivity that can be disseminated. So it lays out what the process should be. It's very logical. It's very it's risk-based. Having said that, public perception is never really driven by good technology or logical thinking. And I think that was my one of my points, right? I think we need to address public perception in ways other than better technical systems. And there's a whole literature on how you do that. And I think we need to learn from that. On your second question around fusion, I guess I would love to talk more with Dr. Zubrin and see how he thinks it's a policy issue. It may be a policy issue in that we are not investing enough, but best I can tell, we haven't, we have to produce more power than we put in, and we haven't been able to do that. And again, maybe it's a policy issue in that if we put more money, we would have better results. So yeah, look forward to that discussion.